Welcome. If you are training large language models using reinforcement learning, you have likely hit the PPO memory wall. Proximal policy optimization is the industry standard for RLHF, but it requires holding up to 4 massive models in memory simultaneously. DeepSeek introduced GRPO, or Group Relative Policy Optimization, to solve this exact bottleneck. By completely eliminating the critic model, while mathematically preserving stable advantage estimation, GRPO drastically slashes VRAM requirements. Today, we will dive deep into the map derivation, the architecture, memory optimization, and debugging techniques for GRPO. Before deriving GRPO, let's recap standard PPO. We typically have an actor model generating tokens and a critic, or value model, estimating the expected return. The advantage function calculates whether a generated action was better or worse than the baseline expected by the critic. Calculating this advantage relies directly on the value model's output. The problem, for a 70 billion parameter LLM, that critic model alone consumes hundreds of gigabytes of VRAM during training, severely limiting your batch sizes and context lengths. GRPO shifts the paradigm by asking, what if we don't need a parameterized baseline at all? Instead of using a massive, separate critic network to predict a baseline value, GRPO evaluates an action relative to a group of peer actions. For a given prompt, the policy generates a group of G different outputs. We then compute the rewards for all G outputs. The baseline simply becomes the statistical mean of this specific group. This profound mathematical shift completely eliminates the value model. Let's formalize this. Given a prompt, we sample outputs E1 through IG from our old policy. A reward system assigns a scalar reward Ri to each output. To compute the advantage for output I, we standardize its reward against the group. We calculate the mean and standard deviation of the G rewards. The advantage AI is simply Ri minus the mean, divided by the standard deviation. This relative scoring perfectly centers the advantages, providing a reliable, zero-mean gradient signal. Now we construct the GRPO objective function. Similar to PPO, we use importance sampling to update the policy. We calculate the probability ratio of generating a token under the current policy divided by the old policy. We multiply this ratio by our group advantage, AI. To prevent destructively large updates, we clip this ratio between 1 minus epsilon and 1 plus epsilon, taking the minimum of the unclipped and clipped versions. This ensures stable, monotonic policy improvement without catastrophic forgetting. Optimizing purely for reward inevitably leads to reward hacking, where the model outputs gibberish that exploits the evaluator. To prevent this, GRPO enforces a callback libeler, or KL, divergence penalty. We anchor the training policy to a frozen reference model. The objective function subtracts a beta-weighted KL penalty, pushing the model to maximize relative reward while staying statistically close to the reference distribution. DeepSeek computes this on a per-token basis to maintain high-fidelity control over the language structure. Mathematically, computing the exact true KL divergence across the entire vocabulary of an LLM is computationally prohibitive. In PyTorch, practitioners use an unbiased approximate KL estimator. This is formulated as the ratio of reference probabilities to policy probabilities minus the log of that ratio minus 1. In practice, you might just see the log ratio used directly. DeepSeek scales this penalty by a coefficient, beta, balancing the model's exploration for higher rewards against the safety constraints of the reference model. So, what does the architectural footprint look like now? In standard PPO, you manage 4 models: actor, critic, reference, and reward. With GRPO, if you use an external rule-based reward system, like a code compiler or a math verifier, you only need 2 models residing in VRAM, the active policy model and the frozen reference model. The policy model acts as the old policy during generation and receives gradients during optimization. This elegant reduction cuts our memory requirements essentially in half. Let's do the VRAM calculus for a 7 billion parameter model. At FP16, the model weights take 14 gigabytes. The Atom Optimizer states demand another 28 gigabytes. Add the frozen reference model, and we are around 56 gigabytes, even before activations. To fit this into an 80 gigabyte HE100 GPU and handle long contexts, we heavily rely on flash attention. By fusing the attention mechanism, we avoid materializing the massive N/N attention matrix in high bandwidth memory, drastically reducing activation VRAM. We can push memory optimization even further. DeepSeek pipelines often employ mixed precision and quantization. We can load the frozen reference model in 8-bit integer or FP8 formats without degrading the KL penalty signal. This shaves off another 7 gigabytes of VRAM. For the policy model, methods like CLORA allow us to keep the base weights frozen in 4-bit, training only a tiny fraction of parameters via low-rank adapters. Combine CLORA with GRPO, and you can comfortably tune massive models affordably. Let's walk through the actual GRPO training loop. Step 1 is the generation phase. We broadcast our prompt batch. For each prompt, we use the policy to sample G-independent responses, where G is typically between 4 and 16. In PyTorch, we strictly use torch no grad here. We gather the generated token IDs and immediately compute their log probabilities under the current policy. These become our old log probabilities, which we catch for the upcoming optimization phase. Step 2 is scoring, where we evaluate the G responses to get rewards and compute the normalized group advantages. Step 3 is optimization. We iterate over the catched data for multiple epochs. We recompute the log probabilities under the actively updating policy, calculate the importance ratio, apply the PPO clipping mechanism, and subtract the KL penalty. We backpropagate this final loss to update the policy weights. Notice how we decouple generation from optimization to maximize GPU tensor core utilization. A crucial insight from DeepSeek's technical reports is that GRPO amplifies the importance of reward design. Without a neural critic to smooth out noisy rewards, your reward signals must be impeccable. DeepSeek heavily leverages rule-based rewards, especially for math and coding. If a Python script passes unit tests, it gets a 1.0. If it fails, a 2.0. This deterministic, high-quality feedback loop is far superior to LLM as a judge for complex reasoning, completely sidestepping the noise of a neural reward model. However, even deterministic rewards can be hacked. A classic failure mode in GRPO is the model learning to output infinitely long reasoning traces that eventually stumble upon the right answer, artificially inflating the reward. To combat this, ML engineers implement length penalties. We modify the reward function to subtract a scalar based on the sequence length. Additionally, format constraints like requiring the final answer inside specific XML tags ensure the model learns structured reasoning rather than exploiting the evaluator. When implementing GRPO in PyTorch, computational stability is your top priority. During the important sampling calculation, use torch exp on the difference of log probabilities rather than dividing raw probabilities. This avoids catastrophic numerical underflow. Furthermore, when computing the group advantage, ensure you add a small epsilon, like 1e8, to the standard deviation denominator. This prevents division by 0 in the edge case, where all generated sequences receive the exact same reward. Debugging RLHF pipelines is notoriously difficult. In GRPO, your primary diagnostic metric is the KL divergence between the policy and the reference model. If your KL drops to 0, the model isn't learning anything new. If it spikes to 10 or higher, you are seeing policy collapse, meaning it has diverged so far from the reference that it's likely producing gibberish. You want a steady, controlled KL trajectory. Adjust your beta parameter dynamically if you see the KL drifting out of the optimal 0.5 to 2.0 range. Another frequent issue is encountering not a number or NaN losses. In GRPO, this is almost always caused by extreme importance ratios exploding the gradients. To fix this first, check your advantage normalization step. Second, ensure your PPO margin epsilon is strictly enforced, typically set at 0.2. Finally, employ aggressive gradient clipping globally using Torch and utils .clipgrad norm. If nans persist, inspect your reward function for extreme outliers that might be skewing the group's standard deviation. DeepSeek's GRPO represents a massive leap forward in the economics of RLHF. By replacing the cumbersome critic model with elegant group relative normalization, it slashes memory requirements while maintaining the mathematical rigor of proximal policy optimization. Combined with deterministic rule-based rewards, flash attention, and careful KL divergence monitoring, GRPO empowers engineering teams to perform reinforcement learning on frontier-scale models without needing a supercomputer. Mastering these techniques puts you at the absolute cutting edge of LLM alignment and reasoning optimization.